It's too bad Mars is such an interesting place, because it's actually one of the most difficult places to visit in the solar system, especially if you want to bring along a lot of luggage. That planet is a graveyard of missions that didn't quite make it. As our ambitions grow and we think about exploring Mars with humans, maybe even future colonists, we're going to need to solve one of the biggest problems in space exploration. Successfully landing heavy payloads on the surface of Mars is really, really hard to do. There are a bunch of challenges with Mars, including its lack of protective magnetosphere and its lower surface gravity, but one of the biggest is its thin atmosphere of carbon dioxide. If you were standing on the surface of Mars without a spacesuit, you'd freeze to death and asphyxiate from a lack of oxygen, but you'd also experience less than 1% the atmospheric pressure that you enjoy here on Earth. And it turns out, this thin atmosphere is making it incredibly challenging to get significant payloads safely down to the surface of the red planet. In fact, only 53% of missions to Mars have actually worked out properly. So let's talk about how missions to Mars have worked in the past, and I'll show you what the problem is. Historically, missions to Mars are launched from Earth during the flight windows that open up every 2 years or so when Earth and Mars are closer together. ExoMars flew in 2016, InSight in 2018, and the Mars 2020 rover will fly in, 2020. The missions follow interplanetary transfer trajectories designed to either get there the fastest or with the least amount of fuel. As the spacecraft enters the atmosphere of Mars, it's going tens of thousands of kilometers per hour. It has to somehow lose all that velocity before landing gently on the surface of the red planet. Here at home, you can use the thick Earthican atmosphere to slow your descent, bleeding off your velocity with a heat shield. The space shuttle's ablative tiles were designed to absorb the heat of re-entry as the 77-ton orbiter went from 28,000 kilometers per hour to 0. A similar technique could be used on Venus or Titan, where they have thick atmospheres. The Moon, without any atmosphere at all, is relatively straightforward to land on as well. Without any atmosphere, there's no need for a heat shield. You just use propulsion to slow your orbit and land on the surface. As long as you bring enough propellant, you can stick the landing. Back to Mars. With a spacecraft hurtling into its thin atmosphere at more than 20,000 kilometers per hour. Traditionally, missions have started their descent with an aeroshell to remove some of the spacecraft's velocity. The heaviest mission ever sent to Mars was Curiosity, which weighed in at 1 metric ton, or 2,200 pounds. Curiosity had the largest aeroshell ever sent to Mars, measuring 4.5 meters across. This huge aeroshell was tilted at an angle, allowing the spacecraft to maneuver as it hit the thin atmosphere of Mars, aiming for a specific landing zone. At about 131 kilometers altitude, the spacecraft would start firing thrusters to perfectly adjust the trajectory as it approached the surface of Mars. About 80 seconds of flight through the atmosphere, the temperatures on the heat shield rose to 2,100 degrees Celsius. And in order to not melt, the heat shield uses a special material called phenolic impregnated carbon ablator, or PICA. Now, this is the same material that SpaceX uses for its Dragon capsules, by the way. Once it had slowed its velocity to lower than Mach 2.2, the spacecraft deployed the largest parachute ever built for a mission to Mars, 16 meters across. This parachute could generate 29,000 kilograms of drag force, slowing it down even more. The suspension lines were made of Technora and Kevlar, which are pretty much the strongest and most heat-resistant materials that we know of. Then it jettisoned its parachute and used rocket engines to slow its descent even more. When it was close enough, Curiosity deployed a sky crane that lowered the rover gently down on the surface. Now, this is the quick version, so if you want an extensive overview of what Curiosity went through landing on Mars, I highly recommend you check out Emily Lakdawala's The Design and Engineering of Curiosity. Now, Curiosity only weighed 1 ton. Want to do the same thing with heavier payloads? I'm sure you're imagining bigger aeroshells, bigger parachutes, bigger sky cranes. In theory, the SpaceX Starship will send 100 tons of colonists and their stuff to the surface of Mars. Here's the problem. The methods of decelerating in the Martian atmosphere don't scale up very well. First, let's start with parachutes. To be honest, at 1 ton, Curiosity is about as heavy as you can get using a parachute. Any heavier, and there just aren't any materials engineers can use to handle that kind of deceleration load. A couple of months ago, NASA engineers celebrated the successful test of the Advanced Supersonic Parachute Inflation Research Experiment, or ASPIRE. This is the parachute that will be used for the Mars 2020 rover mission. They put the parachute made of advanced composite fabrics like nylon, Technora, and Kevlar into a sounding rocket and launched it to an altitude of 37 kilometers, mimicking the conditions the spacecraft will experience as it arrives at Mars. The parachute deployed in a fraction of a second and fully inflated, experiencing 32,000 kilograms of force. If you were on board at the time, you would experience 3.6 times as much force as crashing into a wall going 100 kilometers per hour wearing your seatbelt. In other words, you wouldn't survive. If the spacecraft was any heavier, it would need to be made of impossible composite fabrics. And forget about passengers. NASA has been trying out different ideas to land heavier payloads on Mars, like as much as 3 tons. One idea is called the Low Density Supersonic Decelerator, or LDSD. And the idea is to use a much larger aerodynamic decelerator that would inflate around the spacecraft like a bouncy castle as it enters the Martian atmosphere. In 2015, NASA actually tested this technology, carrying a prototype vehicle on a balloon to an altitude of 36 kilometers. The vehicle then fired its solid rocket, carrying it to an altitude of 55 kilometers. As it was rocketing upwards, it inflated its supersonic inflatable aerodynamic decelerator to a diameter of 6 meters, which then slowed it back down to Mach 2.4. And unfortunately, its parachute failed to deploy properly, so it crashed into the Pacific Ocean. But it's progress. If they can actually work out the engineering and physics, we could someday see 3-ton spacecraft landing on the surface of Mars. 3 whole tons. The next idea to scale up a Mars landing is to use more propulsion. In theory, you can just carry more fuel. Fire your rockets when you arrive at Mars and then cancel all that velocity. The problem, of course, is that the more mass you have to carry to decelerate, the less mass that you can actually land on the surface of Mars. The SpaceX Starship is expected to use a propulsive landing to get 100 tons down to the surface of Mars. Because it's taking a more direct, faster path, the Starship will hit the Martian atmosphere faster than 8.5 kilometers per second and then use aerodynamic forces to slow its entry. It doesn't have to go this fast, of course. The Starship could use aerobraking, passing through the upper atmosphere several times to bleed off velocity. In fact, this is the method that orbital spacecraft going to Mars use. But then passengers on board would need to spend weeks for the spacecraft to slow down and finally get into orbit around Mars, and then descend through the atmosphere. According to Elon Musk, his delightfully unintuitive strategy for handling all that heat is to build the spacecraft out of stainless steel, and then tiny holes in the shell will bleed fuel out to keep the windward side of the spacecraft cool. Once it sheds enough velocity, it'll turn, fire its Raptor engines, and land gently on the surface of Mars. But every kilogram of fuel the spacecraft uses to slow its descent to the surface of Mars is a kilogram of cargo that it can't carry to the surface. There's one more idea, and it's terrifying. I'll explain it in a second, but first I'd like to thank Kimberly Zalski, Quentin Kravacek, Ian Forbes, Dennis Dre, Philip Shane, Wesley Unke, and the rest of our 810 patrons for their generous support. If you love what we're doing, you want to get in on the action, head over to patreon.com/universetoday. I'm not sure if there's any viable strategy that will easily land heavy payloads on the surface of Mars without using propellant. Smarter people than me think it's pretty much impossible without using enormous amounts of propellant. That said, Elon Musk thinks there's a way, and before we discount his ideas, Let's watch the twin side boosters from the Falcon Heavy rocket land perfectly together. And pay no attention to what happened to the central booster. A new study from the Aerospace Department at the University of Illinois at Urbana-Champaign proposes that missions to Mars could take advantage of the thicker atmosphere that's closer to the surface of Mars. In their paper, titled Entry Trajectory Options for High Ballistic Coefficient Vehicles at Mars, the researchers propose that spacecraft flying to Mars don't need to be in such a hurry to get rid of their velocity. As the spacecraft is screaming through the atmosphere, it'll still be able to generate a lot of aerodynamic lift, which could then be used to steer it through the atmosphere. They ran the calculations and found that the ideal angle was to just point the spacecraft straight down and dive towards the surface. And then, at the last possible moment, pull up, using the aerodynamic lift to fly sideways through the thickest part of the atmosphere. This increases the drag and lets you get rid of the most amount of velocity before you turn on your descent engines and complete your powered landing. That sounds fun. If humanity is going to build a viable future on the surface of Mars, we're going to need to crack this problem. We're going to need to develop a series of technologies and techniques that make landing on Mars more reliable and safe and efficient. I suspect it's going to be much more challenging than people are expecting, but I'm looking forward to the ideas that will be tested in the coming years. What do you think? Let me know your thoughts in the comments. Once a week, I gather up all my space news into a single email newsletter and send it out. It's got pictures, brief highlights about the story, and links so that you can find out more. Go to universetoday.com/newsletter to sign up. And did you know that all my episodes are available as an audio podcast too? Search for Universe Today in iTunes, Spotify, or wherever you get your podcasts. Or add universetoday.com/audio to your podcatching software, and I'll put a link in the show notes. And finally, here's a playlist.